Next up, we have Brandon Bestelmeyer from ARS, who has my favorite talk title ever, I think. But maybe now you're going to understand my sense of humor.
This was not the topic to do for an Ignite talk, as it turns out, but I'll talk fast. All right, so big data is promising, but it can also be intimidating and inaccessible, and might at first glance seem incompatible with local science, but I'm going to argue that it is an important tool for scaling up local science approaches. So how does science generally inform stewardship decisions? The usual mode is normal science, which builds toward scientific generalizations with increasing certainty, using highly controlled experiments and consensus within science disciplines. We take those general principles and we offload them via outreach, but the science may not be specifically aimed at decision-making, and the scope may not be adequate for complex problems. So, for example, we know a lot about grassland carbon sequestration. We've integrated in various reports experiments measuring a number of processes like plant growth and decomposition, grazing, erosion, and fire, but does that help you decide whether to add compost to my pasture to sequester carbon? You need to know something about the soil organic carbon responses at that site, nutrient runoff, soil lead, exotic species, and many other effects and values. So it's difficult to inform these sorts of decisions using normal science approaches, leading to the idea of post-normal science in which uncertainty is acknowledged, context matters, and varying perspectives and values are considered. Post-normal science is carried out by extended peer communities involving scientists from multiple disciplines and all relevant stakeholders that develop actionable knowledge given uncertainty, like we heard this morning from the plenary speaker. Local collaborative projects such as CARM, coincidentally just before this talk, are good examples of post-normal science in practice, where you have interactions of stakeholders and scientists in a shared landscape, and data on a variety of meaningful indicators are compared. But the problem, Justin, is how do we scale up this kind of a model? For example, we have 166 land-grant universities plus ARS locations to carry this out, 2 million farms across the U.S., and those would be really big participatory group sizes. So scaling up is going to require a variety of approaches. Certainly we need to train and employ more community-based scientists to carry out these interpretations, but I argue that an organized big data tool set could also be very helpful. Typical uses of big data that can feed this are modeling large-scale patterns by combining large data sets. There's a recent paper in Science that used a large database of bumblebee records plus past changes in temperature to predict changes in richness. And then, of course, we're all familiar with personalized information delivery, marketing, and maybe eventually precision medicine based upon the data that we often inadvertently provide to large data sets. So these same kinds of approaches can promote post-normal science, I argue, by reducing spatial uncertainties in our scientific interpretations, encouraging participatory data collection, and allowing for richer interpretations of management decisions. How do data get big, and how does big data science become post-normal? I think this is what we're all very familiar with in this room. First, starting with standard methods or harmonized data, and that standardization is fundamental to quality information. Then we upscale via training, human resources, and databasing. And this community, and this room in particular, has been very successful in this endeavor, training thousands and generating over 65,000 points of monitoring data globally. We can then link those point data to information databases to generate interpretations like ecological site descriptions, which are in turn produced by these extended peer communities and provide context-specific evaluations. We can also link those point data to spatial layers to create continuous gridded products, such as the Rangelands app that used machine learning to estimate vegetation indicators using remotely sensed data. We can then develop new value-added indicators on top of the vegetation indicators using the point or gridded cover data, such as wind erosion or habitat suitability, and those models in turn are often based on normal science approaches. And then mobile and web technologies can promote scientist-stakeholder interactions. Interpretations can be delivered via web apps and mobile phones, and data can be contributed to improve the quality of information provided. So, I hope I've convinced you that a unified big data framework could provide more information, more utility, and more participation to more people. We just have to feed it with users and ideas and data. So thank you. Yes.
Practical question here. So if some of us are sitting on data sets that are very site-specific and relevant, where should we put them, or who should we give them to?
Sarah.
Okay, thanks.
No, I think, yeah, and to just summarize a little bit, it seems like all the pieces are already here. This community is working on a lot of the pieces. We have collaborative management. We have the landscape data commons that will eventually be able to house all these data, Land PKS, the Rangelands app. But what we haven't done yet is put it all together into a sequence and a package such that it can really inform and generate new local collaborative groups. Yes?
So one of the things that's coming out of big data in other contexts is that if the data that goes in are biased, then you get biased answers for your local situations. How would you go about avoiding that?
How we can avoid bias?
Well, the bias of the data that goes in, or recognizing that bias to make sure that it's not carried over in inappropriate ways.
Well, I mean, yeah, there's sort of the statistical side, and then there's the interpretive side. And I would say on the statistical side, using randomization and spatial randomization, for example, I think is an important way of guarding against the bias that can come from where you put a point, for example, to measure something. But I think it's the collaborative groups, as they work through those interpretations together, that can guard against the personal biases that scientists might have. Okay, those were two.